Okay, here goes our Unit 3 video notes. We have measurement section. Then after that, we have dimensional analysis, which is a majority of the type of math that we do in chemistry. And then we have scientific notation. Okay, so let's go ahead and get started. There's 3 parts of it. So let's start the video.
Why is it important for scientists around the world to use the same system of measurement? One of the steps of the scientific method is to gather qualitative and quantitative data. Qualitative data is based on observations. Qualitative data includes all of the descriptive, observational data that scientists collect during an experiment or study. Qualitative data cannot be counted or measured, and it is usually in the form of written descriptions that a scientist notices during an investigation. Examples of qualitative data include changes in color and odor, as well as formation of bubbles or heat. Quantitative data is numerical data that can be counted or measured. When scientists analyze quantitative data, they compare numerical values by organizing the data into graphs and charts. A spreadsheet is a useful tool that allows scientists to organize their data and create graphs. Scientists measure quantitative data using a system of measurements called the International System of Units, abbreviated SI. The SI system, often called the metric system, has 7 base units that are used to measure quantities. Additionally, each SI unit can be expressed in multiples of tens and tenths of a unit by adding a prefix to the unit. Accuracy and precision are 2 terms that frequently arise when discussing measurements. Accuracy indicates how close a measurement is to the true value. For example, a balance is used to find the mass of an apple. If the balance gives a measurement of 104.8 grams and the actual mass of the apple is 105.0 grams, then the measurement was fairly accurate. If the balance gives a measurement of 99.1 grams, then the measurement is less accurate. Precision refers to the reproducibility of measurements that are taken under identical conditions. If 5 consecutive measurements are taken of the same apple using the same balance, and the measurements are found to be 104.8 grams, 105.1 grams, 104.9 grams, 104.8 grams, and 105.0 grams, then the measurements were fairly precise. If the measurements are found to be 104.8 grams, 100.2 grams, 106.8 grams, 99.0 grams, and 110.2 grams, then the measurements were less precise. Common tools that are used for measuring mass include triple beam balances and electronic balances, which measure grams. The SI unit for mass is the kilogram. Length is usually measured with metric rulers. The SI unit for length is the meter, but kilometers, centimeters, and millimeters are also commonly used. Volume can be calculated a number of ways. The volume of liquids is usually measured in liters or milliliters, and usually with a graduated cylinder or a pipette. When reading the volume of a liquid in a graduated cylinder or pipette, always take the reading at the bottom of the meniscus. The meniscus is the curved surface of the liquid. In a burette, volume is read at the bottom of the meniscus as well. However, remember that the numbers on a burette increase from top to bottom. A burette measures the volume of space above the liquid. This tells how much liquid was dispensed from the burette. The reading for this burette is 7.30 milliliters. To measure rectangular-shaped solids, use the formula volume equals length times width times height. Remember that 1 cubic centimeter is equal to 1 milliliter. Other regularly shaped solids have their own volume formulas. Volumes of irregularly shaped objects can be found by partially filling a graduated cylinder with water and recording the volume. After placing the object in the cylinder, the new volume can be recorded. This is known as displacement. Subtracting the initial volume from the final volume will give the volume of the object. Other devices that are used for collecting quantitative data include Celsius thermometers, which measure temperature, and stopwatches, which measure time.
Dimensional analysis. Okay.
Measurements are very important. Suppose you wanted to start a catering business. You may have to make 350 sandwiches. How would you scale up the amount of chicken needed for a single sandwich so that you purchased enough chicken to make 350 sandwiches? A caterer can use dimensional analysis to solve the chicken purchasing problem. Dimensional analysis is a process for solving problems in which you use a conversion factor to convert from one unit to another. The conversion factor is a ratio of two equal amounts that are measured in different units. The caterer has already created a single delicious sandwich that has 85.0 grams of chicken in it. This is her conversion factor, 85.0 grams of chicken per sandwich. The caterer knows she has to make 350 sandwiches, so she multiplies the known quantity, 350, by the conversion factor, 85.0 grams per sandwich. The conversion factor should allow the known unit to cancel, so that you end up with the desired unit. This equals 29,750 grams, which must be rounded to three significant figures to give the solution of 29,800 grams. In chemistry, grams are frequently used, but in physics, kilograms are common. So for a mass of 29,800 grams, what would be the mass in kilograms? There are 1,000 grams in 1 kilogram. Multiplying 29,800 grams times the conversion factor gives 29.8 kilograms. Conversion factors are a useful tool when converting between different systems of measurement, such as when kilometers is converted to miles. 1 mile is approximately equal to 1.6093 kilometers, so the conversion factor 1 mile per 1.6093 kilometers can be used. 209 kilometers multiplied by the conversion factor 1 mile per 1.6093 kilometers equals 130 miles. 209 kilometers is equal to 130 miles. A measurement may sometimes have a unit that is a combination of base units. For example, the unit for density is grams per milliliter. These types of units are known as derived units. Dimensional analysis can still be used to convert derived units. Miles per hour can be converted to feet per minute. Miles is converted to feet, and hours is converted to minutes. There are 5,280 feet in 1 mile. Multiplying 10 miles per hour by 5,280 feet per 1 mile cancels out the miles unit. There are 60 minutes in 1 hour, so multiplying by 1 hour per 60 minutes cancels out the hours unit. Complete the calculation and you get 880 feet per minute. Notice how conversion factors are chosen so that miles and hours are canceled and only feet and minutes remain.
notation.
The Sun has a diameter of about 1,392,000,000 meters. A yeast cell can have a diameter of about 0.000005 meters. How can scientists easily report such large and small numbers? Sometimes quantities are either very large or very tiny. In these cases, the quantities can be represented in scientific notation. Scientific notation is fairly straightforward. A number in scientific notation is comprised of a coefficient that is greater than or equal to 1 and less than 10, that is multiplied by a base of 10 raised to an exponent. 5.09836, 9.14, 6.02, and 1.0 are all coefficients greater than or equal to 1 and less than 10. 10 to the 5th, 10 to the 4th, 10 to the 23rd, and 10 to the negative 12th are all bases of 10 raised to an exponent. To express 509,836 in scientific notation, begin at the decimal and count the number of digits moved to the left until you reach a number greater than or equal to 1 and less than 10. If we stop here, we still haven't reached a number greater than or equal to 1 and less than 10. So we keep counting. Place the decimal point here, and you have the coefficient. The number of digits you've counted is the exponent for your base 10. Where scientific notation really comes in handy is with very large or very small numbers that have many zeros either right before or right after the decimal. Begin at the decimal and count the number of digits moved until you reach a number greater than or equal to 1 and less than 10. 1.72 is the coefficient, and you write it without the trailing zeros. So 1,720,000,000 is expressed in scientific notation as 1.72 times 10 to the 9th. For a decimal number, you can use the same process, but move to the right. Begin at the decimal and count the number of places moved until you reach a number greater than or equal to 1 and less than 10. 3.6 is the coefficient, and you moved 5 decimal places, so the exponent for the base 10 is 5. Notice that the exponent is negative. Exponents for numbers that are less than 1 and greater than 0 are negative because the decimal is being moved to the right. So 0.000036 is expressed as 3.6 times 10 to the negative 5th. Pause here and use what you've learned so far to express these numbers in scientific notation. Mercury has an orbital period of 87.97 Earth days. What is the orbital period of Mercury in seconds? There are 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. Using this dimensional analysis, we can convert days to seconds by multiplying 87.97 Earth days by the appropriate conversion factors. 87.97 Earth days is equal to 7,601,000 seconds. The result is a very large number, so it can be reported in scientific notation to make the result easier to read. The decimal should be moved 6 places to the left so that the coefficient is greater than 1 and less than 10. The exponent should be equal to the number of places that the decimal moved, and the exponent should be positive since it was moved to the left. 7,601,000 seconds is equal to 7.601 times 10 to the 6th seconds. Using dimensional analysis, the number could be simplified even further by noting that 1 megasecond is equal to 1 times 10 to the 6th seconds. 7.601 times 10 to the 6th seconds is multiplied by a conversion factor to determine that 7.601 times 10 to the 6th seconds is equal to 7.601 megaseconds.